Good evening, and thank you for joining us on Zoom webinar. I'm Eric Walker, Chair of Highlands Astronomical Society, and it's my pleasure to welcome existing club members, new members, several we've got this month, visitors from our North of Scotland sister astronomy clubs and groups, and to the first-time visitors who have contacted us wanting to find out what we get up to, and will hopefully consider joining our wee Scottish Astronomy Club soon. We are buoyed after last month's success in using our own Zoom webinar, so hopefully things will be all right on the night again. Tonight's timings are after this welcome. We will have the main talk followed by questions and answers. Round about 8:30, we'll have club news and Astropics for the month, and then we'll wrap up and take us to the meeting close. We're going, as usual, to have a post-meeting Zoom blether. The link will be provided in the chat box near the end of the meeting, but it's also in the email you received from Rona notifying you of tonight's events. As usual, there won't be any breaks during the meeting, but if you need to leave, just get up and go and keep connected to the meeting. If you've got any questions for the speaker or for the club, please put them into the Q&A section at any time throughout the meeting. Any problems, click the hand icon and someone will get in touch with you directly via chat. The chat for general chit chat has been switched off during the main part of the meeting to minimise distractions, but it will be switched back on near the end. So, what have we been getting up to? As we all know and experienced, the weather was atrocious. Certainly the coldest I can ever remember for May, and the cloud and rain was, shall we say, unseasonable. Even the all-sky camera hasn't had much to show for its efforts. Apart from some interesting cloud formation sequences, in the main it was just hours of solid grey and water droplets running off the lens. Thankfully, enthused by last month's club presentation by Pauline, several of us were spurred on in the first few days of May and managed to capture images of our sun and the planets. Pauline is delighted to be able to show you these later in the evening. Our WhatsApp group conversations quietened down due to a combination of shortening nights, poor weather and lack of observing opportunity, but things are hotting up now, quite literally over the past couple of days. We are eagerly awaiting the first HAS member alert for a noctilucent cloud sighting via the Nebulous News Group, in order we can get our cameras and smartphones out to photograph these beautiful displays. They've already been sighted and photographed from sky by Andy Gray of Glendale Aurora app fame, and Pauline has some of his photos to show us tonight. And so, back to tonight's meeting. I'm going to introduce our main speaker for tonight, Dr. Anna Horleston. Anna Horleston is a planetary seismologist based at the University of Bristol. She studied seismicity on Earth for many years, looking at everything from induced seismicity in the near surface to teleseismic signals that show us the deep interior structure of the Earth. She put that into her bio just to try and catch me out, I'm sure.
Sorry.
For the last 3 years, she's been studying the seismicity of Mars as part of the science team for NASA's InSight mission. She co-leads the frontline operations for the Marsquake service, helping to detect and analyse Marsquakes. She also loves the outdoors and is very sad that she can't come to Scotland to give this talk, because she'd love to get out on the hills. and of course, also to meet us all in person. Anna's talk tonight has generated considerable interest across our amateur astronomy community, and we have several first-time visitors attending to hear her, including one enthusiastic 12-year-old lad and his dad. I'm really looking forward to this talk, Anna, which is about the first and so far only dedicated geophysics mission sent to Mars. InSight has been sending back a near continuous record of the seismic activity on Mars since early 2019, as well as data on weather seen at the landing site. In this talk, Anna will discuss the mission objectives, the seismic data, and what the mission has told us so far about the inside of Mars. Without further ado, I welcome Dr. Anna Horleston and her talk for tonight, Marsquake, NASA's InSight mission to Mars. Over to you, Anna.
Thank you, Eric. Let me share screen and we'll hopefully take it away from there. Let me just double check. Can you see the right screen?
That's all looking good to us, Anna.
Fabulous. And welcome to everybody who's come. I'm really grateful that you've turned up tonight, and especially to our young 12-year-old. I have a 12-year-old son as well, and he has sat through a couple of my talks and he's made it through to the end. So I'm hoping you enjoy tonight. So there's not much to say about my title slide. You've already heard the title and you know who I am and you know who you are. So let's move on, if I can. There we go. Why? Right. Well, I want to go into the why of the mission first. So I'm going to take you through the why. I'll then talk you through how we're going to do them, how we're going to find out what we needed to find out. And then I'm going to talk to you about what we've actually found out and what we've seen with the mission. So let's talk about the why. I used to think that this picture was enough, basically, because, you know, we've all looked up into the sky and seen Mars. And well, I'm guessing, since you're all part of an astronomical society, that you probably all looked up there and a little part of you has wished you could go there. And I'll admit, when I was a kid, I really wanted to go to the moon, actually, at that point. It was just at the age when Helen Sharman was taking her flights, and I really wanted to be up being an astronaut. And, you know, my career path changed a little bit, but the image of Mars has always fascinated me. And boy, do we have some brilliant images of it. But one thing that actually really brought this home even more to me was 18 months ago, literally the last public social event I did before we went into lockdown, I had the opportunity to go to a preview of Luke Jerram's latest exhibition, which is called Mars. I don't know whether you know of Luke Jerram's work, but he's created Gaia and what's it called? University of the Moon, I think it's called, which is where he takes an 8-meter globe, basically, and he projects or prints images, satellite imagery of the planet. So he did Earth, he did the Moon, and this was Mars. So these are all images that we have taken of Mars. And it was suspended in a sports hall just outside Bristol. And this is my son, who had just turned 11 at the time. And literally he and I spent about an hour and a half just wandering around this image of this real, not live scale, but this huge visualization of Mars, and just being able to wander around and look at all the little craters and look at the craters within the craters. And in fact, you can find some places, actually up here, look, you've got a big crater and that's got other craters within it. And there were places where we could find craters within craters within craters, which was so cool. And it just seeing that made me think, yeah, this is why we do it. It's raw excitement of seeing something you've never seen before. That's why we want to go to Mars. And it's why we've gone there a lot as a species. So this image, I first started showing a version of this image 2 or 3 years ago. And at that point, we didn't actually have, I hope you can see my cursor, we didn't have all of these missions up here because they've all landed since. But we've been trying to go to Mars since 1964, 62. And it's not always been successful. In fact, I was saying, sorry, 1960 was our first mission. A lot of the early missions failed. Some of them did manage to at least fly by. So the Mariner missions flew by and took pictures, and Viking 1 and 2. These early missions, I'll talk a little bit more about those later. Those were in the 1970s. They actually managed to land, but then we had a kind of a gap of stuff getting there. And yet some of these spacecraft, even from back here, are still sending us great data. So the Odyssey satellite orbiting Mars has been there since 2001, and it's still sending us data. We actually get our data via the Odyssey lander orbiter. So we've had a lot of missions recently, and in fact, this you'll notice I've had to write Zhurong on the middle because this is this was updated when Perseverance landed, but they didn't manage to update it for when Zhurong landed, which was about 2 weeks ago now. So we've obviously managed recently to get a number of robots onto the surface, and we've had a lot of orbiting satellites taking lots of different imagery. So I know you all like photographs, so I thought I'd put in some images of Mars. So we've learned a lot about Mars just by looking at it from afar, from orbit, and from our rovers that we've got on the surface. So we know that there's a lot of sand. We know that there's ice. So this is carbon dioxide ice in this picture here. So there's so much carbon dioxide in the atmosphere, and it's so cold that condenses out and forms ice. We know that there are stones that show the signs of water. These rounded pebbles were seen by Curiosity, and yeah, evidence of water at some point. And also this crater here that looks a bit like a tadpole, showing this is a water outflow channel from this particular crater. So lots and lots of amazing images, and honestly you could get lost on the NASA websites if you go trawling high-rise images of Mars. I do frequently when I got nothing else to do. I go spend a little while looking at images of another planet. The other thing we have is a brilliant topographical map. In fact, it's the best topographical map of any planet in our solar system. So by topography, I mean the elevation, obviously. So what we're looking at here is high areas are white, and in fact this scale saturates, and Olympus Mons is about 21 kilometers high in total, so it's huge. It's 3 times the height of Everest, and the dark blue colors are very deep. So this is the Hellas crater. This is 7 kilometers deep, and what you'll see is that this is slightly tilted, but most of the southern side of the planet is a higher elevation, and the northern side is much lower elevation and is much smoother. We think this is much younger, whereas here we've got craters pretty much from the birth of the planet. There's been no plate tectonics to wipe them out. The water obviously hasn't wiped them out. The atmosphere has now mostly disappeared, so that's not there to wear things away. So these craters are, from the start of the birth of the planet, really. So best topographical map we have. And we also know a fair bit about the atmosphere. Eric mentioned that we've got enough sensors to be tracking the weather on the surface, but we've also been tracking it from external satellites for many years. So first thing to know is that it's really cold. The average surface temperature is minus 59 degrees, but literally in the course of a day, it can vary from minus 100 to 0 degrees. So every day we see a temperature change of about 100 degrees. Now, I'm guessing that pretty much, actually I've been up to Scotland once, and you do get days where you can start in a valley and it's 25, 30 degrees, and you can get to the top of a peak and it's freezing. So I know that you're used to that kind of an extreme where you live, but that's only 30 degrees. We're talking 100 degrees. And obviously we can't survive those temperature ranges anyway, but it's crazy the way the temperature changes. The other really crazy thing is that the atmosphere is so thin that literally the temperature at your feet is 30 degrees different from the temperature at your head. So the surface of the planet will warm up when the sun shines on it, but the atmosphere is so the opposite of dense. So I've forgotten my words this evening. So spread out that there's not enough atmosphere to heat up to propagate that heat. So literally your head will be 30 degrees colder than your feet. So, feet can be in sandals and your head has to be in a woolly hat. But so there's a very low atmospheric pressure because there's very, very little atmosphere. And there's an awful lot of CO2. Now, anyone following the Perseverance mission will know that they've been trying to split this to create oxygen, which is a really cool experiment. But unfortunately, I'm not here to talk about that. But lots of CO2, not a lot of oxygen, and not a lot of water vapor either. So we know all about the outside of the planet, or at least we think we know quite a lot. But InSight is going there to look at the interior of the planet. And we have this big overarching mission objective, which is to understand the formation and evolution of terrestrial planets through investigation of the interior structure and processes of Mars. So the idea is that we know what's inside Earth, we know what's inside the moon, we find out what's inside Mars, then that gives us a bridge between all these things. And I'll talk a bit more about that as I go through. So we've got three main techniques we're going to use. That's seismology, geodesy, and heat flow, which is how we manage to wangle and rip it all together to come up with our acronym INSIGHT, which is the interior exploration using seismic investigations, geodesy, and heat transport. And I will not be saying that again. We're quite happy just calling it INSIGHT. So to understand why we're doing this, I want to take you back to how a terrestrial planet forms. Now, this is pretty much the most science you're going to get in the whole thing, and it's really not that technical. So a planet forms through, well, this is the way we think they form, through the accretion of meteoritic material. So basically you get a star, and around that star you have a cloud of dust. And as the star formed, that dust starts to spin and kind of coalesce. And as it comes together, it causes a gravitational potential well, and more stuff comes into that ball, so it attracts more mass. And as you get more mass and it's squashing and squashing and squashing, it gets hot in the middle and melts. Just like if you really squeeze your hands together, you'll feel they get hot. Now imagine like a whole world of people squeezing their hands on top of yours. Yours are going to get pretty squashed and probably melted. And then what happens is some stuff happens, and we end up with a planet which has a crust and a mantle and a core. And these have all been differentiated, of course, so they've all separated out. And what we really want to understand by going to Mars is what happens in that stuff happens phase. So on Earth, we're already in this nice crust, mantle, core. Everything's all separated out. We even know we've got a solid inner core and then a liquid outer core. We know an awful lot about the Earth. But on Mars, we don't know what's inside it, and we don't quite know what stage it's got to, or how it got there, or what might happen afterwards. So we want to know what's going on inside the planet. Now, how do we look inside a body? Well, for example, my son was playing rugby on Sunday, and he had a rather nasty tackle with somebody else, and his finger went the way it shouldn't have done. And the first thing we did when we got to A&E was they said, well, we'll take an x-ray of it. And that's how we look inside a body. We take an x-ray. These aren't my son's hands. I didn't get a hold of that picture, I'm afraid, but he didn't break his finger in the end. It's just very badly bruised and strapped together. And it's his left hand, but he's a lefty. So that's quite frustrating for him. But anyway, back to seeing inside things. So what does an x-ray do? Well, an x-ray has an energy source on one side of the body and a film, a photographic plate on the other side. So basically we fire the x-rays on one side, they pass through the body, and then what isn't absorbed or scattered is received by the photographic plate. Now, basically, a seismometer does the same thing for a planet. We put a seismometer on one side, or in the case of Earth, we put thousands of seismometers all over it, and then we have earthquakes, which are the energy source. They send shock waves all the way through the planet, and at those seismometers, we receive different signals. And by looking at the different signals, someone's just sent something to my printer. I'm really sorry about this. If the printer is too noisy, please tell me and I will unplug it. Is that annoying? I can't believe someone's done that.
It's okay, Anna, don't worry about it.
So anyway, so we have these shock waves coming from the earthquakes, and they travel through the planet. And as I say, they get scattered, or they get absorbed, or they don't travel because there's liquid and some of the waves can't travel through that. And then we receive them on the other side, and we can build an image of what's going on inside the planet. So that's how we do it. So it was really obvious that when we started going into space, we would send seismometers. So when we went to the moon with the Ranger missions in the 1960s, we put seismometers on them. They didn't do any good, but we put seismometers on them. The Apollo astronauts, on the other hand, also took seismometers, and those were brilliant because they'd actually put them out on the ground. So you can see here, these are seismometers put on the surface of the moon by the Apollo astronauts. And for 6-7 years, we had seismometers on the moon sending us back data, which was brilliant. And then the first landers we sent to Mars, the Viking landers I mentioned before, they also carried seismometers. There was a flaw with their seismometers, and I'll talk about that later, but we did send them to Mars because we knew that was what we needed to do. So I said Mars is the middle ground. So we've got 100 years of terrestrial seismology. We've literally got thousands of seismometers now across the whole planet. And we know from those that the Earth is a warm planet. It has a liquid outer core. It's got magnetic fields. It's an active planet. It's got volcanoes, earthquakes, and plate tectonics. Whereas The moon, where, as I say, we've had 6 or 7 years of seismic data, and we've also got rock samples that were brought back by the Apollo astronauts. We know that the moon, it's a cold planet, it's solid throughout. There's a remnant of magnetism, but nothing active like we have on Earth. And it's seismically quiet, or geologically quiet. Almost all the activity occurred way back in the past. Mars, on the other hand, is genuinely like halfway in between. It's half the size of Earth. It's big enough to have experienced a really active history. I've told you about Olympus Mons, 21 kilometers high. That is a huge volcano. It's got massive canyons and trenches, but none of it is active anymore. So it's small enough, we think, to have been really hot, lost a lot of heat, and then it's just gone, I've got no more heat, and basically frozen in terms of its geology changing. It's just now, it's not completely solid, we don't think, but it's stopped being geologically active. So we've got a few mission goals. These were our original missions. We've added a couple more in our extended mission that we're now in, because NASA likes to do these things over a couple of years and then change their goals. But their primary mission, we want to find the size of the core. So obviously on Earth, I've said we have a liquid outer core and a solid inner core. We don't know exactly what the core on Mars is, so we wanted to go and find that out. We wanted to find out whether it was liquid or solid and what it's made of. Is it all iron, or has it got other elements in it? We want to know how thick the crust is. So there's a very outer layer of the planet. How thick is that? And how does it have layering within it? And then the same for the mantle. In the Earth's mantle, we have very distinct geochemical boundaries where the pressure and the temperature get such that rocks transform into other rocks. We don't think that'll happen in the mantle in Mars because it's not big enough for that to happen, but we do want to check that that's the case. We also wanted to know how warm it was inside. Has Mars been, was it so hot and then some kind of chemical change changed and so the heat just got trapped inside, or has it just cooled down completely inside? And we want to know, and this is where I really come in, the rate of seismicity. So how many Marsquakes are there, and how often do they occur? And how many meteorite impacts are there every year? Because we'd hoped we'd be able to see those. Now, how are we going to do all of that? Well, InSight's a pretty cool lander. This is a schematic of it, and I'm going to talk you around all the different things on it. So this is just our diagram of it. I will show you pictures of it as we go through, but everything in a NASA mission has acronyms. So not only was it NASA's InSight mission, you got 2 there already, but everything on the mission has acronyms as well. So this here is called IDS, the Instrument Deployment System. Now to you and me, that's a robotic arm. And on the robotic arm, we've got a camera, which is the Instrument Deployment Camera, or the IDC. We've got a scoop, that's just called the scoop, nothing fancy there, and a grapple, that's also just called the grapple. Now the grapple is pretty cool, but also really, really basic. So when everyone goes, oh my gosh, you must have amazing engineering, it's like, well, actually the robotic arm we borrowed from another lander. I think it came off one of the Phoenix landers. It was a flight spare, so it's like 30 years old. The grapple is literally like those claws you get in arcade games, but it's better controlled. So actually when we grab hold of things, we don't let go of them again. But that is the idea. It was simply that we want to be able to pick things up. So all our instruments have little knobbles on the top that we can grab with that grapple so that we can pick them up and move them around. But that was the easiest way to grab hold of everything. A handle wasn't right. We just needed this little grapple thing. So anyway, that's the Instrument Deployment System. And yeah, the actual arm is called the IDA, the Instrument Deployment Arm. We have 2 cameras. So I mentioned the IDC here, the Instrument Deployment Camera. We also have a camera down here, which is called the Instrument Context Camera. And that looks in front of us and gives us a great view in front. But we can't move that one, obviously. Sorry, I double clicked there. We've got TWINS, which is temperature for wind and insight. So that's temperature and wind for insight. So this is 2 wind sensors effectively, but they also measure temperature, and they point in opposite directions so that we can get the wind from almost any direction coming through those sensors. It's really important for us to record the wind, and I'll show you why later, but basically wind can upset our seismic data. So we need to know what the wind is doing to make sure that when we think we've seen a Marsquake, we've actually seen a Marsquake and not just a gust of wind. So that's TWINS. Now RISE, this is a really cool experiment. And I didn't give it enough credit when we first launched. So Rotation and Interior Structure Experiment. It looks really unexciting. It is just, I hope you can see my cursor, these 2 little gray things here that look like speakers. They are actually high frequency radio antennae, and they send out X-band radio signal. and we use it like a GPS tracking system effectively. So by sending out a high frequency signal, we can measure we know exactly when the signal was sent, we measure the time for us to receive it, and we measure the Doppler shift. So we can measure exactly where InSight goes as it orbits, as Mars rotates and as it orbits the sun. That way we can tell how much the orbit of Mars is wobbling. So how much is it distorted? How much does it wobble? Does it wobble with on a large axis of rotation or a small axis of rotation? From that, we can tell whether the inner core or the core is solid or liquid. So it's a really exciting experiment, and yet really, really simple. So that's RISE. We have HP cubed, a heat flow and physical properties probe. This is nicknamed the Mole. It was a heat flow probe that was designed to bury itself 5 meters. Unfortunately, it didn't get that far. I'm not going to talk a lot about this, but if people do want to hear about it, I can cover that in the Q&A. But this was designed to take the temperature. Unfortunately, it's only taken the temperature to this depth, not to the full 5 meters, which is very sad, but a great piece of engineering nonetheless. We have APSS. So basically, when you build a spacecraft, you try and put on as many things as possible. So the auxiliary payload sensor suite also has a pressure sensor and a magnetometer and a couple more temperature sensors, so that we can measure the atmospheric pressure, the magnetic field where we are, and also the temperature. And then we have SEIS, which is the seismic experiment for interior structure, which is basically our seismometers, but we have to give it some fancy name. So there's a seismometer underneath this. This is actually the wind and thermal shield, which is to protect it from some of that daily temperature change that I mentioned. So that was the plan. This is the actual spacecraft. So these are obviously real people. It gives you an idea of scale. These solar panels are just over 2 meters across. Here's that WTS wind and thermal shield. This copper box is actually the seismometer. These are those radio antennae, the RISE antennae, and the white things next to them, those are the twins wind sensors. I don't know what this box is. Must be our comms unit, I think. And this is HP Cube, the Mole, sat on top of the deck, obviously, at this point. So just to tell you a little bit about the inside of the seismometer, this was a multinational, real joint effort. It's actually 2 sensors in one. So we have one sensor that's built very like a normal earthbound seismic sensor, though slightly fancier, with a mass and coil and a magnet and an magnetic force feedback, and that's inside an evacuated chamber here. So this is a vacuum chamber, this gold sphere, and it has 3 components of this, and they're orientated in the UVW axis. And then we have these instruments, which were built here in London, between London and Oxford. They were designed at Imperial College, and they're built in Oxford, and they were tested in Bristol. These are literally about this big. The central plate is about the size of a pound coin. They are etched from a single silicon wafer, and they get mounted on the side. They're called our short period instruments, and they measure high frequency signals. So these ones measure low frequency signals, and these measure high frequency signals. And we put them all together, and we come out with this amazing broadband seismometer. So what's going to create a seismic source of Mars? Well, I said we don't have plate tectonics. That's what normally causes most of the seismic activity we have here on Earth. So there are a few things that could cause seismic activity on Mars. First one is faults. So from all the imagery we've got, we can see clear faults. So normally these bedding planes would run like this, and then obviously there's a fault running straight through here, so that this is shifted upwards and this is shifted downwards. And we've mapped most of the faults on Mars, and we see that some of them are compressional, so some of them are being pushed together, some of them are a bit extensional, so the land is being pulled apart. So lots of fault lines and lots of areas that could show us seismicity. Phobos tide. Now, obviously on the Earth, we have the moon, and the moon is about a quarter the size of the Earth. It's right there, and it causes obviously a huge tidal effect. Now, we don't have that on Mars, but we do have Phobos and Deimos, and Phobos is very small, but it does fly close to the surface of Mars, and we had hoped that we would be able to see a seismic signal from that. I'll tell you now that we haven't been able to detect it. So that was a little sad, but that was going to be a really useful, just a continuous seismic signal we might have been able to see. Atmospheric excitation. You know, I said we needed that wind sensor. This is why, because this is just a simulation of the changes in the pressure in the atmosphere. So basically this is weather, this is wind. So when the wind blows, It obviously blows across the surface of the ground. It causes a pressure change, which causes the ground to move up and down. And we record that, and you will get to hear that later on. So atmospheric excitation is a really big problem, but it's not coming from inside the planet. So I don't care about it. I just wish it would go away. Finally, meteorite impacts. So here you've got two pictures taken from high rise. And this is on the 4th of June 2008, and this is the 10th of August 2008, and you can see this big black cloud here. And if you zoom in on these kind of things, you end up with something like this. This is not that one in particular. This is a better one because I wanted to show you a really good picture of a meteorite impact. But we do see fresh meteorite impacts quite regularly on the surface of Mars. I mean, we've seen many in the course of the mission. And meteorite impacts are like calibration shots. So when you start trying to use a seismometer on a planet, you don't actually know what you're looking at. So you don't quite know how to interpret them. We want to know how fast the seismic waves travels through the planet, but we have to make up a model to work that out. We can say, right, it's taken, you know, there's this difference between the different phases. We think the quake is going to be there. And our models are pretty good. But if we had a meteorite impact where we knew exactly where it landed and when, we would have exactly the travel times that would tell us exactly where things were, and that would refine all our velocity models. We did the same on Earth with nuclear tests back in the 50s, 60s. So it's exactly how we calibrated all our models on Earth, pretty much, is with nuclear tests. So impacts are our calibration shots. Unfortunately, again, they haven't done quite what we wanted them to. We haven't had a big enough one yet, but we're still listening. So the idea behind the whole mission was that we'd put this seismometer there, then the Marsquake service would find and locate Marsquakes. We'd create a catalogue of the seismicity, and then the Mars Structure Service, also known as MSS, would use those locations and phases, and that would get us, we can make that map of the inside of the planet like we make a map of the body with an X-ray or an MRI scan. So that was the plan. So what was the reality? Well, I got invited out to the launch, and I was so excited. We launched from the Vandenberg Air Base on May 5th, 2018. And Vandenberg Air Base is in California. This is their first interplanetary launch from the west coast of the US. And so we got invited out there. We got given these VIP badges. Mine's actually hung up just over there. I can never point in the right direction. Just over there. There it is, behind me. Still goes with me everywhere. So excited. We had to go to a safe area. So we got bussed out to a safe area. The launch was at like 3 in the morning. We were all completely jet lagged, had no idea what time of day it was. Got to this launch site, and they set up these TVs in the field where we were all sat around waiting for it to happen. And we were all kind of like, well, why are we just looking at the TV? And the fact is that if you look at this TV, this is one of the closest cameras they had, and you can still barely see the spacecraft. From the field we were in, there was absolutely no hope we were going to see anything. We could hear it. I mean, not just from the TV, we could actually hear the roar of the rocket going up, but there was no hope of us even seeing the tailbone, which is crazy when you think about that, like the scale of this. And I was really disappointed in a way. I was glad I was there with all my mates, but I found out the next morning that there were a few people in the know who lived in Pasadena, and they'd been up to the hills in California, and here you can see the blanket of cloud and fog that was overlying the whole of California at the time. And this was insight coming out of it. And I kind of wish I'd been there to see that. But, you know, you win some, you lose some. But we launched, and that was the most important thing. And where exactly were we going? Well, I said Mars, obviously. But choosing a landing site is a really, really tricky business, it turns out. And as you can see, this map is a little outdated as well. We've now got Perseverance, I think, is here, and Tianwen 1 is up here somewhere. So where you land on a planet really depends on how you want to land, for starters, and what you want to look for. So a lot of the important things for us, InSight was coming in by parachute. So a parachute requires atmosphere, and I've already said that the atmosphere on Mars is so thin. There's not a lot of it. So you really need to go for a low altitude for your landing. So you don't want to land on any of this red or yellow. You certainly don't want to be up here on the white stuff. I'd love to put a seismometer on top of Olympus Mons, but actually landing it there is going to be impossible. So you have to go for the blue and the green. So we didn't want to go up here, because the second thing is that we need power. We're a solar powered mission. So here's the equator, and you'll notice that a lot of these missions are near the equator. or well, Phoenix obviously wanted to go to the North Pole, and a lot of the others didn't want to live very long. Curiosity's damn lucky because it's got a nuclear fuel cell, so that'll keep going forever. But we are solar panel based, and we wanted to last for at least 2 years. That was our primary mission length. So we needed to be here near the equator. We also needed somewhere level because we've only got 3 legs. And if you try and land a tripod on something uneven, you really don't have much luck. And we had those massive 2-meter solar panels, which were concertinaed up like Japanese fans, and they needed to fan all the way out. And they couldn't do that if we were on a tilt. So more than 15 degrees tilt, we couldn't open our solar panels. So that's why we chose our landing site, really. It was chosen primarily for engineering reasons, just getting us there in the first place. So this ellipse here was our target landing site, and it's about 140 kilometers long. And now, I said I love looking at these images, and I do love looking at these images, but I wouldn't want to have been some of the students who spent 4 years, sorry, I'm going to go back one, just counting all these little craters. There were hundreds. They chose loads of different site areas that we might have landed. This was the best ellipse they could come up with for the trajectory we could come at, and with the fewest rocks. I mean, I don't know why this bit wasn't chosen. This looks even better, but for some reason, this bit was chosen as the best possible site. So you had a sneak preview of this. This red dot is where we landed. Now, when we did this, it was kind of like, okay, why didn't we land in the middle? And then you think, okay, I was told that landing where we did, just hitting this ellipse, was the same as me sat here. I live in Cardiff, so me sat here in Cardiff, getting this was an American who told me the story, so he said a baseball, but let's go with a cricket ball since it's clearly cricket season here, a cricket ball, and me throwing it from here in Cardiff to my sister. Now, my sister lives in Philadelphia, so not just do I have to get it to Philadelphia in the United States, I'd have to not just get it to her house in Philadelphia, I have to hit the full stop keyboard on her laptop, on her desk, in her study, in her house in Philadelphia. That's how accurate I'd have to be. So actually, when I saw this and thought, okay, yeah, you've done a pretty good job then, haven't you, really hitting our exact target? I mean, you probably couldn't read it on the screen on the first one I showed of all the different missions, but there were a number of those who literally flew right past the planet. So we've really come a long way in our guidance system. So we hit the spot perfectly. And within, I think it was 10 minutes, we had this picture. A lot of people said to us, it's all grainy. Well, this picture is from the instrument context camera. So that's the camera on the bottom of the lander. And it had a lens cap on it. And we had literally just fired retro thrusters into a sandy planet. So we had covered it in sand. But the reason we have this photo even at all, and that we had it that fast, is that we also sent alongside us two Marco 1s, they were called Mars Cube 1 satellites. These are literally no bigger than a suitcase. They're about, and I mean a carry-on suitcase, not one of those massive things you take for a month away, a carry-on suitcase sized thing. And they might even be more like briefcase size. They are tiny. And the hours were called Eva and Wally. And I don't know if anyone's seen the film Wally, but in Wally, there's a point where he's flying around and he finds a fire extinguisher. And he lets out a little puff from the fire extinguisher and it sends him off in one direction. Basically, Eva and Wally did exactly the same thing. That's how their guidance system was compressed air. And it's like, oh, we want to go left, right? Okay, we'll pump out a little bit this side, which is why they got those nicknames. But these were designed, they were a test case for our mission. So they launched at the same time as InSight. They flew all the way along just behind us so that as InSight descended, they could be a direct communications link back to us on Earth, rather than waiting for the orbiting satellites to pass over and us having to transfer the signal up to them. We were just able to beam it straight up to Eva and Wally. They sent it back to us, and then literally they just flew right on past the planet and kept going, and we lost contact with them about 3 months later. But they'd done their mission. I felt really bad that we just kind of sent them out. They're probably still, they'll be flying on out of the solar system. It'll take them a while, but they'll be on that course. But yeah, they sent us back this image. So I guess that it was worthwhile. The next morning, we got some more images down via the usual telemetry routes. And this is from the instrument deployment camera. So this is the camera on the robotic arm. You can see the arm. You've got a nice view of the grapple here. So the way we stowed the grapple was that it had its own little ball that it had to catch. That caused us problem at one point. But here's the grapple. You can see it grappled on, that's the word. And here's the scoop, which we use a lot later on. And here's our seismometer. and you can see our adjustable legs so that we can make it the right height. And here's Mars. And this rock here got nicknamed Dwayne, as in Dwayne Johnson, the rock. And one thing I love about this image is that it shows you what a great landing site we came up with, because if you look right here in front of us, it's all smooth. We landed on this beautiful smooth stuff. And you can see other smooth pockets out here as well. But in between all those smooth pockets, there's all this really quite rough ground, actually, which would have been a bit of a problem for us. And these pockets and what we have landed in are what we call they're degraded craters. So they're old craters that have then been filled in by windblown dust. So it creates quite a nice, shallow, smooth place for us to have landed on. So anyway, more pictures. We also sent HiRISE, so this is the high resolution orbiting camera overhead to take pictures. Nothing on here obviously is green. This is just that the camera is saturated because they are so highly reflective. So at the top we have the heat shield that's here. Here is the parachute. You can actually see the full parachute extended out and draped across the planet. And here is InSight. And if you zoom in, you can see it's 2 solar panels are fully opened. And the bright green spot on here is actually where our wind and thermal shield is. That's that white dome on top of the lander. So we knew exactly where we were and we'd landed in a good spot. There were lots of far worse places we could have landed. And yeah, we took a few more photos. And honestly, I got lost spending days staring at these beautiful photos. But we'd got all this way, and this seismometer is still on the deck of the lander. And this was the problem we had with the Viking landers. So a seismometer is there to measure the motion of the ground. But if you look at the Viking lander, these legs have got shock absorbers in them. And the seismometer was up here on the deck. So you put something on the surface of another planet, but then you've put shock absorbers between it and the ground. Now, deploying a seismometer, we'll do this bit first, the wind. So all you record when your seismometer is on the lander is the wind. So this sound file is a little quiet and a little rumbly. It does just sound like, well, like wind, I suppose, like static, like someone blowing on the microphone. But I'm going to play it to you because this is the sound of the wind on Mars. So hopefully you can hear this. You may need to turn your volume up and then turn it down when I flick to the next slide because you don't want me shouting at you. So I'll be quiet to let you listen. So yeah, to do that, we turned up, we had to raise our signal 2 octaves so that it was in the audible range, but that's what you hear when you put your seismometer on the deck of a spacecraft on another planet. What you want to do is get it in the ground. Now, deployment on Earth is really, really easy. I go out to the field, I take a seismometer, so this is a typical earthbound seismometer. I dig a hole for it because you want to insulate it from the temperature changes. You put it in a plastic bag, because that's the most modern way we found of keeping them dry. Put them in a plastic bag, and then you bury it in your hole. You check it's all working. You give it a really big battery and a solar panel to charge it, and you let it get on with its business. And we can do that in an hour, maybe 2, if the ground is particularly hard, or you want to build a fence and keep the deer out or something. This happened to be in Canada. There weren't any deer we needed to worry about on this particular patch, but it takes an hour or 2. Now on Mars, it took us 100 days to do this. So this is a GIF of lots of photos. I should tell you about this rock. Let me tell you about this rock afterwards. But so we had to take lots of photos. It took us 21 days, 24 days or something to get the seismometer actually on the ground. But then we weren't done. This tether had to be released, so the cable, so there was no tension in that. We have this extra loop here that we released. We lowered the leg so that it was closer to the ground. So we tried to pull this cable to open up this loop of cable here. But we couldn't actually hit this pin with our scoop, and then finally we did, and we did it again, but it took a while to actually get the right point. So, and then we had to put down our wind and thermal shield, and this took us, the final release and of this took us until Sol 70, so 70 days on Mars. A Sol is a Martian day, it's 24 hours and 39 minutes and a few seconds, so just a little bit longer than our Earth day. This was the deployment of HP Cube, so that temperature probe I told you about, and you'll see we finally release it, and you'll actually see this move as we do a bit of hammering, and it doesn't go into the ground, it bounces about, so that moves around a little bit. We imaged the eclipses and some sunsets and sunrises. And that's where we got to at day 100. I told you I'd tell you about this rock. So as I said, we got three legs, and landing on a rock would have been very, very bad. Here's our foot, here's a rock. So that's a couple of feet between the two of them. Now this rock is nicknamed the Ace of Spades rock because on the day of landing, one of our colleagues, Tom, he was told that the chances of us hitting a rock on landing were 1 in 52. So he turned to another one of our colleagues, Konstantinos, and he said, Konstantinos, that's like you picking the Ace of Spades out of this deck of cards. And he found out a deck of cards in front of Konstantinos. Konstantinos went bonk and picked the Ace of Spades. So this is the Ace of Spades rock because we didn't quite hit it, but it's right there, and it would have been a problem if we had. And it's been great actually because we've been able to watch dust come and go off it, so it's been really useful for the mission as well. Anyway, we deployed Marsquakes. I'm going to run out of time. I'm sorry. I hope that your deadline, your timing is not too precise, because this is the really important bit. Like I say, with a side order of atmospheric interference. So the way I look at the data, and I do this every day, is I look at things a bit like this. So this is the starting point for me. So this is a spectrogram of a typical day. So I'll talk you through it so that you know what I'm talking about. But at the top, we have literally the waveform. So this is as we go along through time across the day. This is the amplitude of the signal. So we've got two seismometers, so we see the signal twice. And this is the vertical component. So this is the way the ground is moving up and down. In the bottom section here, okay, we have, Sol number. So this is the Martian mission day of the year. So the Martian mission day. So we'd been on Mars 184 Martian days at this point. We also have the time in UTC. So this is, it was June 4th, 2019. So just a couple of years ago, and it was day of year 155. So now this bit here, we've got basically frequency, or the frequency of the waves up here, and the intensity is shown by this color scale. So a brighter color is a noisier signal. So this big yellowness in the middle is wind. It's the middle of the day, the temperature is rising rapidly and then falling, and it's hot and it's windy. So we see lots of noise. These blue bits are quiet bits. So we get to after sunset's around about here, and we suddenly see the temperature drops and everything gets quieter and the wind drops. There are things that are to do with the lander. So these horizontal lines up here, these are called lander modes. So these are resonances of the lander. So just like, like if you flick a glass and it rings, it has a certain note. Our spacecraft does exactly the same thing as well. There are certain bits of the spacecraft that resonate at certain frequencies, and we pick those up by the seismometer as well. And then there's this other resonance here, which we're not entirely sure what's causing it. It might be the ground, it might be the spacecraft. It comes and goes, but it doesn't seem to be temperature dependent like some of these are. So this is very temperature dependent. So those are other things that you might see in the data. And some of these really big spikes, those are glitches. So those are when you turn the radiators on, or you've had your car on and it was a hot day and your engine, or cold day and your engine gets really hot, and then you turn the engine off and you hear bits of the carbonic going pop, pop, crack, and things like that. Or you might hear your radiators do the same. Spacecraft does the same. As it cools down, it cracks, just thermal cracking of the spacecraft, just as it extends and different parts move against each other. And they cause glitches, as we call them, that we can see in the data. So that's what a typical day looks like. Now, to find Marsquakes, we need to look for things that don't look like the typical wind. And actually, there are two Marsquakes in this day here. There's one here and there's one here. Now, it took us a long time to figure out how to do this. I've been doing this for 2.5 years, looking at all these things, finding the Marsquakes. But I promise you, they are Marsquakes. And we've had quite a few different ones. So here's another one. This is Sol number 128. So the 128th Martian day of the mission. And it's hiding in here. And there's another signal I want you to look at here, because you'll hear it in a minute, is this one here. This is the seismic signature of the robotic arm moving. So like I said you can listen to it. So what we can do is we speed up these seismic waves so that we can hear them, because they're much too low frequency. They're only at, between about, up to about 10 hertz. Whereas if you think on a piano, an A on the piano is 440 hertz. So we need to get up a much higher pitch for us to be able to hear them. Again, you'll need to turn this up to hear it. So when I stop talking and press play, you might want to turn your volume up so that you can hear it. There's a very low rumble at the start, and then there's a slightly more coherent signal, and then there's a nice noise where the robotic arm come down. So I'll let you turn up your volume. I'll stop talking, turn up your volume, and then when this slide finishes, turn it down again so I'm not shouting at you. So let's go. Mars wind. That's the Marsquake. A bit more wind. And then we'll go to ground. Okay, turn your volume down. So what you could see there was that the Marsquake, the wind, and the robotic arm all have really different frequency components. They all sound very different. I actually think that the Marsquake itself sounds an awful lot like a tube train coming at you, like that roar of a tube train through the tunnel. But they all sound very different, and they have very distinctive waveforms, very distinctive sound forms, effectively, was the waveform, but which means that we can distinguish them really quite well. We're really good at it. And we've seen others as well. So here's another one. This one is hiding here. This is much more low frequency, so I can't give you a sound file for it because you really wouldn't hear this one at all. If you think the wind's bad to listen to, this is almost impossible to hear unless you've got really good bass speakers. There is a sound file on the website, so if you want to go and look it up, you can find these out. But yeah, they are really hard to hear. I struggle to hear them even with great headphones on. So, but the important things about some of these is that they are really clear seismic waveforms. Now, I know you're an amateur astronomical society, so knowing what a seismic wave looks like or what an earthquake looks like is not your field, but this looks very much like an earthquake. It's actually a Marsquake, but it looks very much like an earthquake because we have two phases arriving. Now these we call the P and the S wave. The one is a compressional wave, so the energy travels like this as the wave propagates like that. The other one is a shear wave, so the energy moves like this as the wave travels that way. So these travel at different speeds. The P wave travels faster than the S wave. The difference between the two of them can tell us how far away the quake is. And these look perfectly like all the kind of quakes we see on Earth, which a lot of the ones we see on Mars don't. This one is beautiful. And it means that we can locate these really well. So what you've got here is a map of the whole of Mars with insights. And then you've got these are our predicted locations for a couple of quakes, including the one I've just shown you. And if we just zoom in on that box, you'll see this. So here's insight, and these are our two best quakes. In fact, we've now got another two quakes, which the data hasn't been publicly released yet, but there are another two quakes which also map to a very similar area. So we could work out the difference in their distance from the difference in those travel times. We could also work out the direction because of the way the particles move. Because we measure them in 3 directions, we could see that the particles have come from a certain direction. So we could actually say, right, they have come from over here. Now you'll see in this map, we've overlain these red lines here. This is a place called Cerberus fossae. Cerberus fossae is a huge network of fissures in the surface of Mars, and they're up to 1,000 kilometers long. So these are huge. That's like from me to you. It's that far away. So huge cracks in the ground. But also very narrow cracks in the ground. And we thought these might be seismically active because we've seen rock falls or imaged rock falls within them. And there's also water outflow from them, which may or may not be that recent, which might be caused by the seismic activity. So we thought this would be a good place, and it does look like it is. We've got now, I say, several quakes that seem to come from this area. So it's really cool because we've got imagery and we've got seismic waves. The other really interesting thing I said about the Marsquakes was that they look a little different from the earthquakes often. So this is a comparison. So from looking at these quakes, we can tell a lot about the structure of the of Mars. So these are earthquakes. So this figure was made by my friends in Zurich, where they work on they spend half their time looking at Marsquakes and half their time running the Swiss seismic survey. So in Switzerland, they have a lot of small quakes like this. They're very short, last about 30 seconds, and they're just very impulsive, don't cause any damage. No one really notices they're even there, but they are there. They're just popping off. And then you get what we call teleseismic events. Sorry, I threw that word in my biog and I caught Eric out. Teleseismic. So a distant quake, basically like television, teleseismic. We can measure the movement of the Earth from a long way away. And these last, oh, no, go back. Sorry, I have a very sensitive touchpad here. These last a few minutes, and you see, like I said, the P waves and then the S waves. And in fact, we see other waves as well, but we haven't seen those on Mars, so I won't tell you all about them. And then we have a Marsquake, and as I said, this looks like the teleseismic quake. We have the P waves and the S waves, and they last maybe 15 minutes, maybe 30 minutes, maybe an hour. On the moon, we have all these quakes, which are just very, very scattered. So the signal is just very diffuse. And basically what we think is happening is obviously the Earth's quite wet. We have a lot of water both inside the planet and on the surface of the planet, which means that when the Earth gets fractured, say from a quake, it also can heal itself, which is why you might see veins of different rocks within others. That's because water has helped those minerals to move, to migrate, and to form. So you might get a nice quartz vein where you had a fracture. The moon doesn't have that water. So when it gets bombarded by meteorites and it gets cracked, it just stays cracked. And Mars is somewhere in between. And when you have that cracked structure, you know, the signal just, every time it hits a crack, it bounces in a different direction. So the moonquakes, the signal is literally bouncing all over the place. In the Mars, it's bouncing slightly less, and in Earth, it's able to go, okay, yeah, I'm just going to go straight on through, which is why we see these really clear signals. So the type of signals we're seeing can tell us an awful lot about the structure. Now, I really do have to hurry up. So our biggest enemy is dust. Now, I showed you that beautiful image in the clean room of the spacecraft before we launched, and you could see our beautiful solar panels. And here they were 10 days into the mission, still pretty much black and shiny. By 220 days into the mission, we were looking a little dusty. In fact, this is even now last summer, it's even worse now, but we were looking like this. Now, dust is a serious problem for solar panel missions, and we had thought that we would be able to clean our solar panels, just like Spirit and Opportunity did for many, many, many years longer than they should have. Because there were these things called dust devils, so little spinning vortices, pressure waves, that like literally little tornadoes that spin along the planet and pick up dust. And we could see the tracks of these. They literally, as they go, they're like little hoovers. They run along and they pick up dust. So you can see all these different lines. And you can see the InSight lander here. And it's like, well, surely these must be passing by. And we measured them on all our sensors, but none of them was clearing any of the dust off the solar panels. And this is a really big problem for us, because if you cover your solar panels in dust, you don't get power. Now, one thing we've been doing this year is we were having problems. I said we had those glitches from things expanding in the heat or shrinking in the cold. And one of the things we thought might be causing that was our tether, so the cable between the seismometer and the lander. So we had this mission to try and bury it. So we're using our scoop to dig up little scoops of soil and drop them onto the tether. And to make sure we got as close as possible, we started by dropping them onto the wind and thermal shield. And what we saw was that not only did it clear where it swept off, that's where it literally went, gravity just, we dropped it here and it swept straight down, and it cleaned this section of the wind and thermal shield, which was getting covered in dust that was just falling out of the atmosphere. But more importantly, the lighter dust that didn't fall straight was getting blown, I've lost my mouse, here it is, it's getting blown across and bouncing off here. And you can see these little bright spots where the dust was bouncing off and clearing away the dust underneath. And someone had this bright idea of, why don't we just drop dust near the solar panels and let it blow across in a kind of sandblasting way? Now, I'm afraid you can't tell anyone about this outside this meeting until maybe a couple of days when NASA are going to tell the world about it. But we tried this last weekend, and there were lots of people on Twitter going, well, what have they done? Who's programming that robotic arm? They've dumped mud on the deck. What if they've made their solar panels worse? Because yeah, you can just look at our lander. It's all very, very dusty. Everything's covered in dust, but we dumped this extra pile of dust on the lander. But the important bit about these two pictures is that here's our solar panel and it's this kind of reddy color. And here's our solar panel and it's a kind of blacky color. And if you remember, our solar panels are black. And what we discovered is that this dust, we dropped it over here, but the lighter particles blew across here and they bounced and they took some of the dust that was there with them. And it has actually given us a small power increase, which is really important because we are running out of power. So we're actually going to try this again in another couple of weeks. It does seem ridiculous. Yeah, we're just going to throw more dust at something, but it is clearing our solar panels. We can only reach a very small area, but it will, even getting 4 or 5% more power is enough to see us through where we are now, which is aphelion. We're at the furthest point from the sun. We're at very cold. It's the winter. We can't put our heaters on because we don't have enough power. But just getting an extra 4% will keep us going for many more weeks, and might get us through aphelion so that we're then coming back towards Mars, and it might see us through another many months of mission. So crazy as it sounds, throwing dust at something seems to be clearing it. So again, yeah, don't tell anyone, but I got to wrap up. So it's Sol 893. We've been there 893 Martian days. We've taken 5,900 photos, and they are all available to see the moment we get them on Earth. So if you go to the website, you can go and look at them, and go and spend the rest of your week looking at images of Mars. It's definitely seismically active. We've seen 4 quakes that we've located to Cerberus Fossae. I know I showed you the map and we only had 2. We've got 2 more, but I can't show you exactly where they are. And we've also got a handful more quakes that are located near that. And we've used a lot of those quakes. And I told you at the beginning that we wanted to find out the size and the state of the core and the mantle of the crustal structures. And we have actually done that. But we've written 3 papers and they are all just waiting to be published by Science. And I can't tell you the results until they are. So in the next month or so, there'll be a press release about it. So if you follow me on Twitter, I will tell you all about it. So we do know what is inside Mars, or at least know a lot better than we did. And we've learned that throwing dust at some things can make them cleaner. I mean, don't tell your parents you're having a dust bath, but it can make a difference. So I'm going to stop there finally. I'm sorry I've overrun. Thank you very much for listening. This is an image taken today on Mars. This was 893. So this is where we're at. And if there's time for questions, please, yeah, now's the time.
Oh, thank you very much, Anna. Can you hear me?
I can, yes.
Yeah, okay. I had trouble with my voice to begin with. I've always wanted to ask this question. Excuse me. Engineers seem to be very important in these missions. Do astronomers and geologists become engineers, or do engineers become geologists and astronomers?
Oh, that's really interesting.
You see what I mean?
Yeah, I do. I mean, I've found it fascinating because obviously I came at it from as a seismologist. There are a lot of us scientists who have been sucked into the operations side. So the mission has very much, we've got the operations team who do all the engineering, but then we actually, I was trying to explain this to my husband the other day, we then have science team meetings where we say, we really want to look at this today. So we want you to program that to do it. So the engineers then had to go, oh, okay, we'll figure that out. So I think it's very much a two-way street, and who actually, I think, I'd say you're more likely to, I don't know, it seems like everyone at JPL has a really big crossover, and we all feel a bit like engineers now. We're like, well, we know the robotic arm can't do that. So no, it's too cold to do that. And it's fascinating the ridiculous things I now know. The operating temperatures of the seismometer on Mars, I can tell you all of those. Yeah, so this kind of a mission sucks you in and makes you a jack of all trades, I think. And especially I noticed actually on the science side of it, certainly there are many people on many different missions. So a lot of our team are migrating towards Perseverance now, or they're working with Ingenuity and things like that. So it's like they are, there are huge crossovers, even though they seem like completely different missions. The science and the engineering all comes together.
Good. Thank you. Thank you. What's the download time from Mars to Earth?
So the straight download is 8 minutes, but actually so when we record it on the spacecraft, we record it. In fact, our data we decimate as well. So we record it 100 samples a second. We then decimate it down to 20 samples a second. We then have different uplink and downlink buffers. So our uplink buffers, our downlink buffers, we actually have like the high priority, medium priority, and low priority. So we can say, right, this is not major priority. It's going to sit in the medium priority buffer until someone asks for it. A high priority one, we then have to wait for a satellite to fly overhead. And then that satellite then has to get to the right point to transmit back. So typically I have about a 6-hour delay on data, and I'll get data at the start of the mission. We were getting data 3 or 4 times a day. At the moment, we're getting it once or twice a day. So I get kind of a day's worth of data, and the latest bit of it will only be a few hours behind where I am.
Mm-hmm. Okay. And does the temperature variation, you were describing the big temperature drop, does that affect the signal quality at all?
That doesn't seem to affect the signal quality, no. I mean, it affects our data that we're recording, but it doesn't affect our transmission of it, no.
Okay. Another question, is InSight close to any other Mars mission equipment, and can it detect them?
It's not close enough for anyone. Like we all kept saying, oh, why can't Perseverance or someone come and clean our solar panels for us? But they're not close enough to come and do that. Oh gosh, is this embargoed? I can tell you that we listened for the landing. Sorry, it's ridiculous. We've been writing papers on things. I'm not allowed to talk about the results.
We won't say.
I know the landing of Perseverance and the landing of Zhurong, the Tianwen-1 lander. We listened for those with our seismometer. I don't know whether anyone has seen now. What was it called? Was it Away? There was a Netflix series where people were trying to go to Mars, and they basically they were on their way to Mars, and they thought their ship had crashed. Their relay, what was the word? The supply ship, which was supposed to go out ahead of them, they thought it had crashed, and they said, "That's great, we'll pull up InSight and they'll tell us whether it landed or not." It was cool that we got name checked and that they did look at seismic data, but we'd hoped that we would be able to see the impacts from some of the actual flight stages of, for example, the Tianwen-1 landing and the Perseverance landing, but we've not had great success at seeing those. I think I can say that. So yeah, nothing else is communicating. We are attempting to get some dual science though, because obviously we've got pressure and temperature sensors and some of the other landers have. So we're trying to get dual measurements as well so that we can compare what we're seeing in different places.
Question from Matt. These quakes at Cerberus look really close to InSight. Is this just happy coincidence, or is it likely the quakes are very common across the planet?
So we did land quite close to Cerberus, so that because we thought it might be a useful site. We don't know. We expect that there are quakes happening across a lot of the planet. Certainly, there are other fracture systems that could be causing quakes, and all our models now, where we say we think there's this much seismicity, are based on the idea that they are happening over most of the planet. So yeah, a bit of both. We did try to be there. We're glad we're seeing them. We're glad they're coming from where we thought they would come from. But yeah, hopefully they are coming from other places too. But we can't be sure.
And another question is, there's lots of questions for you. Is there any hope of getting a second seismometer at another location on Mars? Do you know if that's planned?
There were plans. I can't remember. So the one we've actually got was originally supposed to be on the Russian mission that blew up in the 90s. So this was supposed to be, we were supposed to have had two now already, effectively. There was originally a plan to send one on the Rosalind Franklin rover. I don't think it's now going, because I met the team who've got our seismometer when it was supposed to go on Rosalind Franklin. So the SP, the short period instrument done by the guys at Imperial College, I met them, yeah, way back when Rosalind Franklin was first proposed as a test run. But I don't think Rosalind Franklin is now going to take one. But there is another joint mission coming, I can't remember what it's called, which might have a seismometer as well. But I'm not sure that we're going to have two running at the same time, because looking at the dust coverage, it's likely that we're going to die before that happens, which is very sad.
Okay. Now, Pete asks, is the sky crane type of landing now going to be the preferred way of putting rovers on the Mars? Because there used to be a very high failure rate at putting down equipment, and it seems to be quite successful now.
I would guess they will gravitate towards that, certainly. I mean, InSight, obviously, we just came in hot. We just flew straight in, and we didn't go, I don't think we even went around Mars. We just went straight in. We were like, okay, here's Mars, we're going in. I saw the entry, descent, and landing video. You know how NASA likes to dramatize these things. I saw that the week before and thought, oh my God, especially because I was going to be stood up in front of a whole audience giving a talk and then feeding the live stream. I was like, this could be the worst day of my life. But so I was amazed when it worked. But yeah, the sky cranes are amazing. Watching Perseverance and even seeing even the advances in things like the video technology, watching them lower Perseverance. That was, yeah, I'm very jealous of that mission. I'd love to be working on that too. But
are there any surprise results from your studies so far, if you're allowed to tell us?
I can tell you one from the magnetics team, actually. So we put a magnetometer on basically as an extra, because we're like, oh, we'll just throw it on. And they've discovered the magnetic field, or at least the local magnetic field around where we are, is twice the strength of the field that had been measured by the orbiting magnetometers. So it's more like a field strength that you might see on Earth, but it's very localized around us as far as we can tell. So that's quite an unusual result. I think the diversity in the Marsquakes is unusual. And certainly when we first saw them, it was a bit of a shock because we'd planned, we had this whole procedure. We literally did test runs where we created test data, assuming the noise level on Mars and then putting in basically what an earthquake would look like. And then we got there and it was all like, well, these look like moonquakes, not Marsquakes, not earthquakes. So that was quite a shock to us. The other results are kind of in line with what we'd hoped to see. Our models seem to have been pretty good, and what we get from them is consistent with what we'd hoped we'd see, and results for the core radius and the composition are in line with what we hoped we might find. So nothing else crazy.
If you happen to be on Mars, would you be able to feel these quakes? Are they not very
no, they're more like magnitude 3s, so no, you'd have to be right on top of it to really feel it.
Okay, let's see. And there's a question about, could any of the Marsquakes be related to meteorite impacts?
We are looking into that. So I did have one extra slide that I left out because I knew I wouldn't have time, where we had one impact which arrived, now how far away from us was it? It was like 40 kilometers from us. And we hoped we'd be able to see it, but we couldn't. But that said, we do have a series of quakes that we think might be meteorite impacts, but we can't quite confirm yet. So we have a number of sightings and quakes that are within the right time window. Part of the problem we've got at the moment is that when we get a notification of an impact, we get a time window. So that time window could be anything from a month. So obviously it's when one photo, there's a difference between one photo and the next photo. And that could be anything from a few weeks to a few years. So it's saying, right, okay, well, we've got this 3-week window when this impact should have happened, and we've got 5 quakes that happened in that. So it's a bit of a, we're trying to do a matching up game at the moment. But if we can match up enough, then I think that, we might well have seen a few. So we're fingers crossed, that would be a great result.
Yeah. And another geological question, what is the cause of the faulting? You know, the big faults, the faulting.
The cause of the faulting. We think it's to do with basically just the kind of, well, there's a couple of reasons. The big faults, so where we've got Cerberus fossae. Cerberus fossae was almost certainly there because of underground lava, which we don't think is flowing anymore, but a bit like you see these kind of formations in Iceland. So where the lava is underground, then the rocks just fall down on top of it, basically kind of melts the ground above, and then you get these big channels. So we think there's kind of residual stress from when that formed, because we can see fracture tips growing as well. So obviously they're moving. The other thing, the smaller faults, we think might just be cooling of the planet. So like you'd take a cake out of the oven and it would collapse and cool and crack on the top. Same thing's happening to Mars. It's cooling and cracking. So there's a combination of effects. There's a third one as well, which is the topographical loading. So, you know, I said that the southern hemisphere was much higher than the northern hemisphere. So there's a lot of land mass on the southern hemisphere. And that's obviously pushing down, and that's causing flexure. So there, a lot of different reasons could be causing them. Cerberus fossae, likely ancient volcanism, but we don't think it's active at the moment.
Okay, it's rather like lava tubes collapsing, things like that.
Yes, yeah.
Do you know how deep the bedrock is beneath the lander from the seismometer readings?
We've got a couple of guesses. So there's the surface of Mars has on the very top there's lots of dust, and then there's rock. Now we've got a couple of readings from the seismometer which put different boundaries at something like 4 or 5 meters. There's just this dust bit, and then we hit rock, we think, which is an ancient lava flow, and that's also backed up by impact craters. So we've got imagery, you saw some of the images, loads of images of that area where we can see the bottom of the crater effectively, and you can see where rocks have been ejected out. So obviously if the meteorite got through a certain level of dust, then you hit rock, and then you get rocky ejecta rather than just dusty ejecta. So the depth we can see into those craters gives us an idea. And across most of where we are, we think it's about 3 to 5 meters of dust before we hit this ancient lava flow that's kind of like red bedrock, I guess.
Now the last question is, what about the future? Any exciting missions ahead or ideas?
Oh, well, from me or from them? I mean, I'm very excited to see what's happening with Perseverance. I'm very excited to see what's happening with Rosalind Franklin. So what was it? It was meant to be meant to go last year. Should have arrived at the same time as everything else has. I'd love to see the results coming back from that. I'm excited by what's going on, say, with Ingenuity. I love your backdrop, by the way. And it will be interesting if we can get any of the data out of it to see what the Zhurong, the Chinese rover, is doing. We're hoping, that there's certain embargoes on data exchange between the US and China, but not so much between us and China. So we're hoping to get to see some of that data. And beyond that, yeah, gosh, I would love it if someone else would take a seismometer. That would be amazing.
Okay. Thank you very much indeed.
Oh, thank you.
Rona, thank you for handling the question and answer session tonight. Some fascinating questions as usual. And my goodness, you had your work cut out tonight. What a questions. Thank you very much for everyone for contributing to that. Anna, I'd just like to take this opportunity to thank you. That was a most interesting, captivating, and my goodness, are you enthusiastic or what? Really, really good.
It has been said.
I'll tell you what I was impressed very early on with. You had the Mars globe basically stitched together. Yeah. I saw a huge moon globe when I was at the Orkney Science Festival, and it was the Lunar Reconnaissance Orbiter images, and I was absolutely taken with it, and I couldn't work out what I was looking at and where I was. Seeing something in 3 dimension versus what I'm used to observing the moon and imaging the moon in 2 dimension, flat. Oh, it's so different. Oh, I'm really impressed. I'd love to see Mars, actually.
Yeah, it is amazing. Honestly, you could just lose days wandering around it, looking at all the different features on it. It was just, I just didn't want to leave when we were there. So, yeah.
And thanks for answering the question about the upload and download, upload link and downlink speeds. Just to let the audience know, before we went on air, Anna let us know that she says, my data comes from Mars. I was most impressed by that statement. Yeah. Now, Anna, pre-COVID times, you would be here receiving enthusiastic, rapturous applause, and you'd get a token of our appreciation and a thank you card designed and printed by Pauline. We're just going to have to send them to you the old-fashioned way. Okay? Yeah. But thank you very much once again. I hope you can stay with us and experience the rest of our club meeting.
I'd love to hear it. Yeah.
Well, it's down to us amateurs now, but we're also enthusiastic, as you'll see. So anyway, thank you very much, Anna.
Thank you.
And now we're going to go over to the club news and Astropics from the month. Pauline's with us once again, and she's going to show you what our club and other amateur astronomers and observers in the north have been getting up to. She's got several beautiful and interesting images to show you. But first, she opens with a short educational piece for us amateurs about the inner planets in our solar system, which we can observe for ourselves. Pauline, over to you.
Thank you very much, Eric. Right, I thought I would talk about conjunction and elongation in respect of the inferior planets. Now, the inferior planets are Venus and Mercury, and of course they're not really inferior. It's just the term that's been given to them because they happen to lie between the Earth and the Sun. So they are our innermost planets. Planets from Mars outwards are known as the superior planets. I thought the best way to talk about conjunction and elongation would be to describe the way Venus moves around the Sun. And what I say about Venus just about applies to Mercury, at least most of the time. First of all, though, we need to consider our position on Earth. And when we're facing the Sun, we are facing south. That means we have east on our left and west on our right. So this too would be the eastern side of the Sun, and this would be the western side of the Sun. When Venus or Mercury is at this position, it's called superior conjunction. Now, conjunction simply means that two bodies happen to be very close to each other in their line of sight. So here we've got the Sun and Venus, They look as though they're together, but we know they're separated by millions of miles. And it's the same as Jupiter and Saturn, the conjunction of Jupiter and Saturn that took place in December last year. They looked very close to each other in the sky, but again, we know that they are separated by millions of miles. So when Venus or Mercury are in this position, we cannot see them in our skies on Earth. And then that's because, of course, Venus and Mercury would be in the glare of the sun. So Venus travels in an anti-clockwise direction. And as it moves away from behind the sun, if we look in our western sky, we can see Venus just popping up above the horizon. Now, this might seem a little bit odd, Venus in the west, and yet I've already said to you, this would be considered east of the sun. So why is that? Well, if you look at the Earth and think about the way it rotates in an anti-clockwise direction. So as it turns away from the sun, we experience sunset. So anything on this side of the sun would then be seen in our western sky. Venus and Mercury both have phases, very much like our moon. And if we used a telescope to look at Venus, because most of the sun's light is reflecting off the planet, it would look like a fat gibbous that we've got here. But because it's so far away from the Earth, it actually isn't quite as bright as it can be. And Venus is an extremely bright planet, but it's going to get a bit brighter. So as it continues to move in its orbit, it moves outwards, or at least it appears to move outwards as it orbits the sun. It's not really doing that, of course, but from our viewpoint, that's what it looks like. And if we look at Venus in the western sky, we'll see that it's getting higher and higher each night. If we looked at it through a telescope, then we would see that its phase has changed to a fat half. Eventually, Venus reaches this point here, and this is called greatest eastern elongation. So this is the greatest angular distance from the sun as viewed from Earth. And if you notice, it's not directly sideways. It's slightly down a bit because that gives you then this greatest angular distance. And this is also when Venus reaches its highest point in the night sky as viewed from Earth. And Venus, of course, is getting closer to us all the time. And as it gets closer, it gets brighter. And I should have said, despite the phase reducing to a half. So Venus is waning, and yet it's getting brighter. After greatest elongation, Venus now moves gradually down towards the western horizon as the nights go on. And through a telescope, we can see that Venus has changed to a very bright, large crescent. And you can see that here. And compared to the size of Venus when it was a full Venus or even a fat gibbous phase, this crescent is enormous. So that's a lot of light that is reflecting is reflected from the sun towards us. And that's why, even though Venus is merely a crescent now, it is very bright in the sky. As it gets closer to the Earth, of course, the crescent is going to get thinner, and only at that point does it begin to dim a little bit. And then Venus ends up between the Earth and the sun, and this is known as inferior conjunction. We cannot see Venus in our sky because no light is reflected towards us. It's like a new moon. But just as we can sometimes see the new moon, as in a total solar eclipse, we can sometimes see Venus crossing the face of the sun. Of course, you need a carefully filtered telescope for that. And that would be a Venus transit, but these are very rare. They only occurred twice in 100 years plus. So that doesn't often happen. Venus usually passes under or over the sun. And as it emerges on the other side of the sun, it becomes a morning object. So there it is, low down in the eastern sky. At first, a very thin crescent, which then thickens up and it gets that little bit brighter. But as it moves away from us and as it gets a bit higher in the morning sky, it begins to dim. Once it reaches greatest western elongation, which remember is its greatest angular distance from the sun as viewed from the Earth, it reaches its highest point in the morning sky, and it now shows a half phase, getting dimmer all the time. After greatest western elongation, you'll see that Venus gradually drops lower and lower to the eastern horizon. It's still in the morning. It's getting less bright, and it's now at this gibbous phase, but it's a lot smaller than it was when it was a crescent phase. Now we're back to the beginning, superior conjunction, where Venus is hidden by the glare of the sun, and it's nowhere in our sky. Just a little bit further on, and now we see it once again in the western sky just after sunset. This is the position of Venus at the moment, which is why it is so low down in our western sky. This diagram, I should point out, is simply to show you, or to give you an idea of what Venus is doing. So its phases and the fact that it moves up, reaches its highest point and then moves back down again. And when Venus was on this side, I merely reversed the diagram and the arrows, but you'll see in a couple of slides' time that Venus actually has some very strange movements in the sky if you actually plotted where you found it. So to summarize, the phases of Venus are smaller and fainter when full or gibbous, because Venus is furthest from the Earth. And then when Venus is a crescent phase, it's larger and brighter, apart from when it's very close to the Earth. And of course, it's brightest because it's closest to the Earth. You probably know or will have heard that Venus is known as the evening and morning star. This green area here shows you when Venus is hidden in sunlight, and that's when we can't see it in the sky. And numbers 5 and 8 show your greatest eastern and western elongation respectively. Now with this diagram, it's a little bit further down than in my diagram, which I've got a little bit further up, but it's near enough. So these are some of the really peculiar movements of Venus. So these shows what you can get in the sunset sky, and this shows you morning sky at sunrise. So this one at sunset is near enough what I showed you in the diagram, but you can see that sometimes it doesn't seem to do an awful lot, and other times we have this really peculiar movement of Venus. Now, even though Venus is very low down on the western horizon, it will get higher, and greatest eastern elongation is due right at the end of October, and by then we should be able to see it a little bit better. So if we look at some sky stuff now, don't forget your summer triangle with Vega, Altair and Deneb. That's nice and bright in the sky. And there's Arcturus in the constellation Boötes, and that is really quite bright. One of the brightest stars in the sky. Remember, it's the 4th brightest star. So we've got new moon on the 10th of June. Now, 2 weeks ago, there was a lunar eclipse, which we couldn't see because it was daytime and it was really only visible for those people in Australia, New Zealand and certain parts of Asia. And always you'll find 2 weeks later, you will end up with a solar eclipse. Now, we don't see the full, a total solar eclipse, but we do get a partial eclipse. So that's on the 10th of June. And then we have full moon on the 24th of June. So it's not a solar eclipse, a total solar eclipse that we would normally expect, where the moon completely covers the sun. Instead, we have an annular eclipse with this beautiful ring of fire around it. And this is because the moon has an elliptical orbit. So sometimes it's close to us. And 2 weeks ago during the lunar eclipse, that was a supermoon. And that was when it was that little bit closer to us. So it appears a bit bigger in the sky. And then other times it's just that little bit further away. And when that happens and it passes in front of the sun, it doesn't quite cover the sun. So we end up with this annular eclipse. We, however, end up with a partial solar eclipse. So the more north and west you are, the more the moon covers the sun. We are a bit luckier than England and Europe in that we have 35% coverage, which is quite nice. What I don't like is where it says this day was cloudy 86% of the time since the year 2000. So that's a little bit disappointing. So Thursday, 10th of June, the first contact occurs at 8 minutes past 10 in the morning. And you can see the direction of the moon. We have maximum eclipse at about 20 past 11. And then it gradually moves away. End of eclipse is about 12:30. So Eric hopes to live stream the partial eclipse if it's sunny. If it's cloudy here, but sunny in Caithness, then Gordon Mackey from Caithness Astronomy Group hopes to live stream it. So you might be lucky that way. But otherwise, there will be plenty of live streams on the internet. So if you get a chance to see the actual annular solar eclipse, then it would be worth looking at because it will be really beautiful. But one of the nice things to do when it's a partial solar eclipse, at least, is to project the image. Now you can use a pinhole, but using binoculars, and Dave explained this a couple of months ago, you actually get a bigger image to be able to see the partial solar eclipse. So you just cover up the big side of the lens, or the big lens, one of the big lenses, point that towards the sun, make sure that you move it around so that you line up the binoculars, get the smallest shadow you can, and that means that you'll project the sun onto a white piece of card. At no time look through the binoculars, you will go blind. And then make sure that you move the binoculars away and back again so that you don't melt them. If you've got an old pair of binoculars, probably a good idea to use those. So we have no Mercury at the moment. And although Mars is low in the western sky, you won't see it because it's so bright. Venus, as I've said, is very low down on the horizon, but it is rising steadily. Trying to see it in our light skies is difficult. Around 11 o'clock at night might be a possibility. Whether or not you'll see a really thin crescent moon, maybe. If you use binoculars, as long as the sun has gone down, then you should see both Venus and the crescent moon. And there's a good view of Jupiter in the morning, shining at minus 2.5, so it's nice and bright, easy to see. Best time is 3 o'clock, but the time gets earlier because Jupiter rises earlier each night. Saturn rises, or at least the best time to see Saturn is about 1 o'clock in the morning. And again, Saturn will rise earlier and earlier, so it will get to a more decent time. But of course, at the moment, at this time of year, these two planets are probably there at the best time of night when it's reasonably dark. Don't bother looking for Saturn when you've got any part of the moon close by. And this is the lander from China that Anna was talking about that's landed on Mars. And the amazing thing is that this is the first nation to land something on Mars other than America. So this was a tremendous success, especially considering they don't have that much experience with landers. So they've done extremely well. I rather liked this. I got this from Space Weather, and it shows a solar flare being produced from the vicinity of this sunspot here. And this was photographed by an amateur astronomer from his garden observatory in Switzerland. Now, as Eric was saying, don't forget to look out for noctilucent clouds. They are around, as we know from the photographs by Andy. Thought it was Andy Stables, but so you're telling me it's Andy Gray, right? And they were first seen on the 20th of last month from Canada. So they should be becoming more visible as time goes on, although I didn't see any last night, despite having a clear sky. So we're on to club news now, and this is the patch that Eric and his team of Dave, Matthew and Lisa have designed, which is rather nice. And this means it'll be all right on the night, so very appropriate. So I'm going to say something about the observatory. Last month I told you that we had a water leak. That's now been fixed, so that's good. And the other thing that we were hoping for was to have something done about this path, which is potholed and muddy and waterlogged and pretty horrible. This is my weird diagram. So here's the observatory. There's the main car park, and that's the path that we use at the moment. Now, this is where they're hoping to put in an overflow car park. Rona and I went to meet the manager last week, and he was saying they have permission to build the overflow car park to about this level here. But he's going to see if it's possible without, because we said, yes, please. He's going to see if it's possible to extend the car park all the way to the boundary fence. That would mean that they would take away this stand of trees, which is just beginning to interfere with our eastern horizon from the telescope in the dome. But it would be fantastic because we could park the cars here. They would build us a new path so that we could get to the observatory quite easily. So absolutely brilliant. And this is just a grassy bank which hides the overflow car park to a certain extent. And of course, this is only going to be used when they get really busy in the main car park. We're still waiting for the Puriflow system to be serviced. Guys, very busy. Arthur had a lot of books, and many of them were on astronomy. Lorna, his wife, would like each member to have one, certainly for those who knew Arthur, because we know that a number of you didn't know him. So what I'm going to do is to send a list of books when I send out Stargazy Pie in the next couple of days. It'll be first come, first served. So please put down 4 choices with your first choice on top. Now, if you want to find out a little bit more about the books, then all you do is to Google them, because there's bound to be information about them on the internet. We're going to keep back 4 to use in an auction, and this is to raise some money for the club, and we think Arthur would approve of this. So on to the gallery of photographs. Now, I have been told in no uncertain terms by Anthony that I raced through them, so I've got to slow down. So the first 4 are from Nora Watson, and these were photographs of the aurora taken in April, which unfortunately weren't able to be shown in last month's gallery. So these are beautiful, and they're overlooking Cromarty. So you can see the oil rigs. And in this photograph, you can actually see Cassiopeia. This is Dave's photograph of Capella, which is a nice bright star in the north at the moment, and it's a star that I was saying that you often see when you see noctilucent clouds. And he took this with his Nikon camera with a 300mm lens. And he used the same equipment for the planetary photographs. So here is Jupiter at dawn. Now, Dave has been complaining that the skies have been too light to be able to see Jupiter and Saturn, but he's managed. So this is absolutely brilliant. So here's Jupiter, and here is a close-up. And here is Saturn. And if you look carefully, you can see that Saturn has an elongated shape. And if you can't see that, put your glasses on. This is a beautiful picture by Mick O'Donnell. Here we have the crescent moon with Earthshine and Mars. And I think this is the double star that Mick is referring to, Mebsuta in Gemini. And if it's not, Mick, please put something in the comments. And here we have Mercury, which Dave managed to capture. Now, Mercury is very elusive, difficult to see, let alone find. So Dave has done incredibly well, and he's managed to get Mercury 3 days in a row. So at the beginning of the month, it was at its brightest, fading gradually, but at the same time getting higher in the sky. Oops, there we go. So in some ways easier to get as it gets higher, but in other ways more difficult as it gets fainter. This is a really good one of Mercury. And then we have Venus. So again, Venus has been very difficult to photograph because it's been so low down on the western horizon. And I cannot see Venus with the naked eye, certainly couldn't at that time. I found it with binoculars, and I knew it was in this area, and I think these are the lights of Craig Fabric. So it was somewhere there, so I put my telescope on it. It's just an 80mm telescope, attached my Canon camera, and there you go. So I did actually manage to photograph Venus. I was particularly pleased about that. Now this is photograph from Dennis. Dennis has a number of observatories in his garden in Port Mahomet. His BAA director of comets, I think. And he has captured supernova in this beautiful spiral galaxy called NGC 3147, which is found in Draco. So that is a tremendous photograph. And here we have the sun by Dave. And you can see the two sunspots on it. Now he used his TAL 150mm telescope and a small camera, which variety of which has just escaped me for the moment. And he's enlarged the area where the sunspots are found. So this is 2822, and here is 2823. And this is near the beginning, well, a week or so after the beginning of the month. And here is 2822. So that was the upper one, wasn't it? Yeah. Taken by Eric. And this is with his hydrogen alpha telescope, whereas Dave was using a solar filter to photograph the photosphere. So with the hydrogen alpha telescope, you are photographing the lower part of the chromosphere. So that's just above the photosphere. These are wonderful prominences that Eric has managed to capture. So this particularly fabulous grouping here, and then you've got a number of smaller prominences you can just see on the edge here. And then at the end of the month, Neil Weston from Sigma has captured two more sunspots, 2824 and 2826. And the detail in this, I presume this is a hydrogen alpha telescope, it's just phenomenal. It's really beautiful. So these are the noctilucent cloud photographs by Andy. So it's grey then, not stable. So sorry about that. And this was taken on the 24th of May. And another one here. Of course, it helps when you have this glorious background, but you can see the clouds here are really quite subtle. And this particular photograph was sent into space weather. So this was 2 days later. And I don't remember us having clear skies, but maybe we did. But it's absolutely beautiful. And Eric found this photograph on Facebook. We're not sure who to attribute it to. I think I've seen it in the New Scientist magazine, but I can't fully remember. But it's pretty good. So there we go. Thank you, everyone.
Well, thanks very much for that yet again, Pauline. As usual, a perfect balance of education, practical astronomy for us amateurs, club news, and wonderful images. I knew that Dave Davidson wouldn't be able to resist your challenge of planet hunting. And thank goodness he didn't, because I thought we were going to be a bit shorter images, although we weren't at the end of the day. Again, a fair variety of images received from our enthusiastic band of amateurs this month. Very impressive considering the conditions we had and the little time window we had. Just a couple of corrections were due and apologies to make. You're right, Pauline, it was Andy Stables from Sky.
Oh, good.
Yes, Andy Gray was a guy I used to work with many years ago, actually. And Neil Weston's from Aberdeen Astronomical Society.
Oh yes, and of course I should have remembered.
Yeah, I know we met Neil.
Sorry,
Yeah.
Neil. Right. I will correct that.
Anyway, thank you very much for that, Pauline.
Thank you.
Well, that's just about us for tonight. I just want to thank our technical support people, the Haas Tech team, for working so hard in the background, both prior to this meeting and also to tonight. The night may be finished for most of us, but if you want to join us for a wee informal blather, please click on the link which should be shown in the chat box, but it's also in the email that you received from Rona or one of us notifying you of tonight's events. After you've clicked on the link, you'll see a screen or a box saying that the meeting is yet to start, and it'll take a couple of minutes for me and Matt just to close down this meeting and open the chat room. So just hang about for a wee while until it does. To all of you, thanks once again for coming along. Until the next time, clear skies and keep looking up.